And we're back. Welcome back and happy Tuesday. Today, we'll continue on and finish up our material on support vector machines. Before we begin, project number 3 on logistic regression will be due Thursday, 7th, coming Thursday, at the usual 1 second before midnight. That's 11:59 and 59 seconds p.m. So why don't we continue? When we last left off, we talked about the primal form, and this was the Lagrangian formulation, where we included our maximization of the margin. That was our primary objective. It was expressed as a minimization problem, and that was what that 1/2 W transpose W is. We got that from our geometric formulation of the distance that the nearest off-plane point makes with a hyperplane. And so that first term in the Lagrangian is finding the max margin hyperplane. Now, we included with that the slack associated with each one of the data points from our sample, and this yn W transpose xn plus b quantity minus 1, that was what we called the slack. And that slack is equal to 0 for points that are on the margin, or those points that are nearest to the hyperplane. And we had a Lagrangian variable, our alphas, that modulate that slack. And so this represented originally an inequality constraint that we expressed as an equality constraint and use this Lagrange variable to absorb that extra amount beyond which some off-plane points make beyond the margin. And so we add that up across all of the variables, this Lagrangian slack, modulated by the Lagrange variable. We negate it because we want to put this in a minimization problem. We want to maximize this quantity in a minimization problem, so we negate each one of these terms. Okay. We could also think of this objective as encoding the idea of get the classification correct. Now, we said we take this expression, the Lagrangian, sometimes called the primal formulation, and we take or solve this minimization problem by setting the gradient with respect to our variables of interest, W and B, and then we take these results from this minimization problem with respect to W and B, we substitute back in to this Lagrangian to get the dual formulation, and that resulting dual formulation we maximize with respect to these alphas. So we're solving two problems, two optimizations, a minimization with respect to WB and a maximization with respect to our set of alphas. Okay, and so we talked about this idea of a saddle point being that solution where we have two different optimization problems that tug against one another. So why don't we continue on with our exploration of the Lagrangian. So in our formulation of the support vector optimization problem, we started out with our minimization, which represented maximizing the margin or finding the hyperplane associated with the maximum margin for the closest off-plane point. Now this was our primary objective, and we started out with an inequality constraint that encoded this idea of getting the classifications correct. And so let's look at what calculus tells us when we have an optimization problem that is subject to an inequality constraint. So here we have the blue curve, and that's going to be our objective function. In this particular case, it's a parabola, it's a quadratic. And we also have a first order constraint, and this first order constraint is an inequality constraint that says we want to constrain our solutions X for this problem, our feasible points, such that X is less than equal to some value we're calling Z. And that is represented as this red line, our first order constraint. Now, of course, if we look at our unconstrained solution, we're finding some x where the blue curve finds maximum, that's going to be this point A on the blue curve. But if we include that inequality constraint, our first order constrained maximum is now this point B, because we want to make sure that that x that finds the maximum point for that function, x cannot be greater than z. It's less than equal to z. And that's going to be this quantity B here along the blue curve. It's also that point where this red constraint line intersects with this blue primary objective, our function of interest. And so if we look at our function, this particular quadratic, ax squared, we get for ax squared equals some constant. Depending on that constant, we get a set of concentric functions here. And so if that constant is smaller, we get a smaller version. If it's larger, we get a larger version. So what calculus tells us is that as we perform the minimization or the maximization, we're basically walking the gradient that's tangent to the surface of this function. Now for the unconstrained solution, this gradient is 0. We get the turning point for our function. If our constraint is at most z, well, we get a different gradient. And so we're always going to walk a gradient that's tangent to the surface of the function. Now, of course, for the unconstrained solution, this gradient is at the top of this function where it's equal to 0. But let's add in this constraint. What happens? Well, when we add in this constraint, we notice that the solution point where f of x increases, our quadratic, and g of x decreases, it's balancing that optimal solution, that intersection point where the red constraint line meets the blue curve. It's different from that unconstrained solution. So essentially that constraint wants to take our gradient and pull it down, down, down in the left-hand direction. And so one of the gradients for maximizing the unconstrained problem for the function wants to pull our solution to the right, and the other force in play, our constraint, our inequality constraint, wants to pull our solution at the same time to the left. And where we reach a feasible point that satisfies both that optimization, maximizing the point for the blue curve, as well as the constraint at most z, it is achieved where we get this equilibrium between these two forces. And so this is the function. F of x wants to bring that maximization solution this way. Likewise, that constraint wants to take that maximum solution and bring it in the other direction. And where we get equilibrium, where these two forces, the tugging to the right and tugging to the left, where they equal 0, is the solution to that constrained version of the problem. And so essentially, we balance these two competing forces, and where they come to 0, they reach equilibrium. That is our solution to the constrained problem. So this is what calculus tells us, and this point is the saddle point. It's where the gradient that wants to pull you one direction and the gradient that wants to pull you in the other direction reaches an equilibrium point. It's also called the Lagrange point. So this saddle point, going back to the saddle surface, we have one derivative with respect to one variable, wants to pull the solution higher, and the other derivative with respect to the other variable wants to pull the value lower. And this equilibrium point, the saddle point, is where those two competing forces balance out. And that's what the Lagrangian optimization approach gives you. And so this idea of Lagrange point is not new. It comes from physics, specifically from classical mechanics. When you have a mass-containing body, there's a gravitational attraction between any two mass-containing points. And so in classical mechanics, the Lagrange point is where celestial bodies are affected by gravitational attraction that comes to rest or equilibrium or stable position. Now, of course, here we have the sun. The sun has mass, and points in space that contain mass are going to, near the sun, are going to want to come closer and closer and closer to the sun because of Newtonian gravitational attraction. Likewise, the Earth, it has mass, and therefore it's going to exert gravitational attraction on mass-containing bodies. Now, of course, the gravitational attraction of the Earth is smaller than the gravitational attraction of the Sun, hence the Earth orbits the Sun. But there's a point at which, if you look at that force that wants to pull you towards the Sun and that force that wants to pull you towards the Earth, there's a point where those two forces tugging in opposite directions reach an equilibrium, and that is the so-called Lagrange point. Now, of course, the Lagrange point is useful for things like geosynchronous orbits for satellites. If you put a satellite right at the Lagrange point, the satellite can maintain orbit without using fuel. And you notice it's closer to the Earth because the Earth's pull is smaller than the Sun. If you had an equidistant between the two, well, the Sun's gravitational attraction is larger, and it's going to want to pull that point in towards the Sun. And so this idea of Lagrange points originates from classical mechanics, and it's these stable points where the gravitational attraction cancels out in both directions that are pulling. And so the method of Lagrangian optimization gives you these saddle points, or these so-called critical points, which is what we use in machine learning. So Lagrange points has to do very much so with machine learning, specifically one of the techniques used in support vector machines. And so here we have some maximization problem. That's our objective. And we have a set of constraints that we've converted to equality form, as we did when we coined the term Lagrangian slack. And so we solve for the saddle point by maximizing with respect to a set of variables. Now, of course, for this maximization, it was converted to a minimization problem. And then we took the result of this maximization and we substituted back in and then solved another maximization with respect to another variable. And we used, in support vector machines, a quadratic programming solver because it's a quadratic programming problem and is very efficient in finding solutions to quadratic problems. Okay, and so going back to our Lagrangian formulation, let's continue on with the formulation. And we have our primal problem, which is a function of three free variables, our parameters W, weight vector, B, the bias term, and alpha, our vector of big N many Lagrange variables that modulate our N many expressions for slack for each one of our in-sample points, Xn. And so if we take the gradient with respect to W and B, we get two solutions. One, the gradient of Lagrangian with respect to W is just W, because we have this W transpose W that looks like W squared, so it's 2 times W. So we get W minus, if we take the gradient of the second term, that set of slack variables, those slacks, Lagrangian slacks, added up. If we look at this expression, we take the derivative with respect to W. The only term here that involves W is our alpha n yn W transpose xn. Everything else goes to 0 under this gradient because, for all intents and purposes, it is a constant under that derivative with respect to W. So that being the case, we have our sum, alpha n yn W transpose xn, that W is to the 1 power, so we're left with a sum, alpha n yn xn. And there's our minus sum. For little n goes from 1 to big N, alpha n yn xn. We set that gradient equal to 0. The second gradient that we have is with respect to B, the bias term. Now, all of these terms will drop out to 0 if we take that partial with respect to bias, except for this one term that involves the bias that is our sum, alpha n yn times B. Everything else drops out to 0. That B is to the 1 power, so we're left with the sum, alpha n yn times 1. And so here we have minus the sum, alpha n yn, that's the gradient. We set it equal to 0. So now we're going to take these two solutions set to 0, those gradients with respect to our weight vector W and with respect to the bias term, and now we're going to solve. So this gives us two equations that we're going to use and substitute results back into the primal formulation, back into our Lagrangian. So we get W is defined as the sum for n goes from 1 to big N, alpha n yn xn. And then we have this other term our sum, n goes from 1 to big N, if alpha n yn is equal to 0. So if we do this substitution, let's start with our substitution of W. We substitute our W, well, we substitute here, and we substitute here, we notice we have this double summation. So the first substitution, we're going to call that summation index n. The second substitution, we're going to call that summation index m. And that gives us a double summation with respect to n and with respect to m. And we get yn, ym, alpha n, alpha m, xn, xm. And there's our expression. Now you notice here, we have our double summation. Now this double summation here, we're going to carry forward, and then we're going to look at the substitution of this second result from the gradient of the primal problem. That is the sum, n goes from 1 to big N, alpha n yn is equal to 0. So if we look at this, well, let's look at this second term from the Lagrangian. We have an alpha n yn, and we have times all of the things in this first parenthesized expression. And then we have an alpha n times this minus 1. Now, of course, everything, alpha n yn, W transpose xn, alpha n yn, b, involves an alpha n yn. If we substitute the sum, alpha n yn is equal to 0, everything's going to cancel except for that term, which is the alpha n times that negative 1. And so what we're going to do then is we're going to put in this substitution, cancel out those terms, and we're going to get a minus alpha n times a minus 1. So that's going to be plus alpha n. Okay. So our result then, all right, well, we're going to have our double summation, our 1/2, that's double sum, and that 1/2, that double sum, we're going to subtract from that. We have an alpha n, yn, xn, and then we also have a W substituted, and that's another sum, alpha n, yn, xn. So that particular aspect of the sum, well, we're going to get a 1/2 of that double sum, and we're going to subtract from that one of those double sums. That's a negative 1/2 of that double summation. And so here, this alpha n, yn, W transpose xn, that's going to give us this minus 1/2 double sum. N goes from 1 to n, m goes from 1 to n, of yn, ym, alpha n, alpha m, xn transpose xm. The term that comes from this summation of alpha n, yn, b, well, b is a constant, we're going to use that substitution for the sum alpha n, yn equals 0, and that term is going to cancel out, and we're left with this sum of minus alpha n times minus 1. That's that positive sum alpha n. Now, this expression has a name. It's called the dual formulation, and it's a function of alpha only. We substitute it in using our primal formulation back into the Lagrangian, and we came up with this function of just alphas being the only free variable. All the x's and all the y's, those are constants that we get from our data set, our in-sample points, our labels, and our instances. And so now we take our dual formulation, and we're going to maximize that with respect to our alphas, our Lagrange variables. Now, it has a constraint. These Lagrange variables, we know from our Lagrangian slack that they're greater than equal to 0 for each one of our in-sample points. We also know that the sum of all the alpha and yn, because that's part of our solution from the primal problem, is equal to 0. Now, we're going to use this sum alpha and yn equals to 0 as a constraint for this maximization problem using our alphas as our feasible solutions. And then we're going to set the fact that our alphas are greater than equal to 0. So now, if we have this maximization problem, we can find the equivalent maximizing alpha if we multiply this by -1, turning it into a minimization problem, and multiplication by -1 is a monotonic transform. And so if we do that multiplication by -1, this is our equivalent minimization problem. So we're minimizing, finding that alpha that minimizes 1/2 double sum, n goes from 1 to big N, m goes from 1 to big N, of yn, ym, alpha m, xn transpose xm, minus the sum of all of the alpha n's. And so the nice thing about this form is that this is a quadratic programming problem. We have this quadratic term in terms of our alphas, because it's multiplied by another alpha, and we can input this into a quadratic programming solver. Now, the reason for multiplying this dual formulation by -1 is because QP solvers, quadratic programming solvers, only do minimization. So we convert this. Okay, so when we look at this, we're then going to take our set of coefficients and pass them to a quadratic programming solver to find the alphas that solve this minimization problem. And this is our decomposition. And so if we write all of our coefficients in matrix form, this is what it looks like. So we take all of our yn, yms, our xn's, xm's, and we can read those off from the data, and we populate a coefficient matrix. We're going to call that Q, and then we're going to multiply, left multiply by alpha, and we're going to right multiply by alpha, and then we're going to encode our linear constraint in vector form. So here we have our linear portion. Here we have a quadratic portion. It's alpha times alpha, alpha transpose coefficient matrix times alpha. That's our quadratic component, set of coefficients, quadratic in alpha, with our linear component. And then here is our constraint, the alpha and yn summed are equal to 0. And so for the bound on alpha, we don't set an upper bound. Upper bound is infinite, but the lower bound is 0. Alpha is always non-negative. Okay, so this coefficient matrix is then input into our quadratic solver, and we then get back from the solver our alpha vectors that give us our solution. And so in our solver, that's 1/2 alpha transpose, our coefficient matrix alpha, minus 1 transpose alpha, subject to y transpose alpha, where all the alpha are greater than or equal to 0, or at least 0. So now, when we run our solver, it's going to return to us our vector of n many alphas. And from that solution, we can go back to our result from solving the primal formulation and actually construct what our weight vector W is. Our weight vector W is just going to be the sum, given all these alphas, of alpha n, yn, xn. Now, of course, we know that when we formed our equality version of our inequality constraint, we had our Lagrange variable alpha times what we call the Lagrangian slack. And we know that for the points that are on the margin, our slack, this term, alpha n times our slack, is equal to 0. Because our margin point had this expression was equal to 1 in the equality sense, and we said that we can scale our hyperplane up and down so that for the closest off-plane point, i.e. the point on the margin, that this expression is equal to 1. So we know that for this Lagrange variable times the slack to equal to 0, either the slack is non-zero, that means our alpha n, a Lagrange variable, has to be 0 for this product to be 0, or if you are a margin point, the slack is exactly 0, and this alpha is greater than 0. So what does this mean? So what it means, for all those points that are on the margin, those closest off-plane points, we have alpha n is greater than 0. But for all those other points, so-called interior points, that are not on the margin, not closest to the hyperplane, their alphas are going to be 0. And so that means when we define our weight vector, this weight vector is going to be a linear combination of those points xn that are on the margin. All those points that are off the margin, the interior points, their corresponding alpha is going to be 0. So they're not going to contribute to the definition of the weight vector. So it says when you're describing the hyperplane is going to be defined uniquely in terms of the so-called margin points. And those margin points have names. They're called support vectors. It's all of those points whose alphas, their Lagrange variables, are non-zero. hence the name support vector machines. Okay, so given these support vectors, we can then take our solution, solve for W, and then take one of these vectors, xn, and solve for B, because we know that yn W transpose xn plus B is equal to 1. So we take an xn as corresponding yn, we take the W that we solve for, knowing our support vectors by linear combination, and then we just solve for B to get our bias term. Okay, and so when we look at our support vectors, they're called support vectors because you can think of them as holding up the hyperplane. It's holding it up by its margins. And so in this depiction here, the purple line is our hyperplane. We have our margin, and we have all of our xn that are on the margin. They're those points that are off plane, that are closest to the hyperplane. And so these xn's, they're responsible for holding up the hyperplane. Hence, the definition of a hyperplane is by weighted combination of these margin points. Okay. Now, the interesting part from a complexity standpoint is that this gives us a high-dimensional model, but we only pay our complexity in terms of a relatively small number of margin points, which is kind of nice. You can also take this linear model through a nonlinear transformation and get the benefit of highly complex decision boundaries, but only pay the cost complexity-wise in the VC dimension sense of the word. You only pay complexity in terms of a small number of support vectors. And so we have our dual formulation again, and we took the negation of that so we can input into a quadratic solver. And we then collected our coefficients, which are the y values, our labels, and the input feature vectors. And we solved for our values of alpha. And so here, if we look at the dual formulation, if we notice here, we have xn transpose xm. That's an inner product. If we compute our phi function to carry our decision boundary, our hyperplane, from original input space to some high-dimensional z space, all we're doing here is computing our phi on xn transpose and our phi function on xm transpose. So the only difference between a hyperplane, a linear model, in input space and feature space is the definition of inner product. It's now inner product in z space. And so this idea then of drawing a nonlinear decision boundary using support vector machines is quite interesting. Now we can draw a highly nonlinear decision boundary in feature space, but only pay the cost of a small collection of support vectors in terms of the VC dimension. All right. And so then in Z space, we know that the hypothesis, and therefore the support vectors in the nonlinear phi function case, they live in Z space. And in order to get those equivalent points in input space representation, we would take the inverse mapping phi inverse to give the pre-image of our support vectors. And it'll help you to visualize, but it's important to know that these support vectors, through our nonlinear transformation or phi function, they live in Z space, but you can view the pre-image of these support vectors. And so a generalization result for this nonlinear case says that our expected out-of-sample error is at most proportional to the number of support vectors divided by n minus 1. And what this says is that we can draw a very complex nonlinear decision boundary with a lot of degrees of freedom, but pay the cost in the complexity sense of the word in terms of only a relatively small number of support vectors. Pretty powerful. And we'll talk about that in detail in a subsequent module when we talk about kernels, a very clever way of doing this phi function transformation without actually performing the mapping. Okay, so with that, we will end there. And as usual, please stay healthy, stay safe, and I will see you all on Thursday.